Thank you. Good morning, everyone. So, I am an Inspire faculty fellow at IIA in Bangalore, and today I will be discussing about the work that I have been doing, studying primordial gravitational wave spectra from cosmological scenarios. So, this talk, the results that I will be presenting in this talk will primarily be based on these papers that I have shown here. So, okay, so let me just dive right in. So you must have seen this kind of plots several times. So this shows the various kinds of sources that we can have for primordial gravitational waves and the wide range of frequencies that these gravitational waves cover. And also it gives you an idea of which upcoming or current gravitational wave observatories can detect these signals. So for the purpose of this talk, I will be interested in gravitational waves that arise from quantum fluctuations in the early universe. So we are basically talking about these. And as you can see, they cover a very wide range of frequency. And so these, the primordial scenario I will consider can be inflation, for instance. And the observatories that I will be talking about, the gravitational wave observatories, will primarily be LISA and Einstein telescope. And I will briefly also mention nanograv, but you have already heard from Rajiv about detection of these stochastic background in the PTA, by the PTA data. So this is a very brief overview of how we calculate this primordial gravitational wave spectrum in standard cosmological scenarios. So this is the equation of motion for this primordial tensor fluctuations in the absence of any source. So we do not have a source term on the right hand side of this equation. So we can solve this equation to get the tensor modes and then using the solution for that we can calculate the energy density that is contained in these gravitational waves. That energy density is this rho GW. After that we take a derivative of this rho GW with log k and take a ratio of that with the critical density of the universe, and that gives us what is known as the relic energy density in the gravitational waves. And for the purpose of observations, the quantity that we are interested in, that we want to evaluate, is what is known as the fractional energy density in gravitational waves as evaluated today. That is why we have this superscript 0 here. And under certain assumptions, under certain simplifying assumptions, this can be expressed in this manner. So we have this PT. PT is the primordial tensor fluctuation spectrum, and if it is let's say arising from inflation, this is nearly scale invariant, and that is what I will be assuming in this talk. That this is nearly scale invariant. This is a ratio of these degrees of freedom. This is a ratio of the temperature today compared to the temperature when these gravitational waves were generated, horizon crossing basically, and also the ratio of the Hubble parameter or the expansion rates at these two different times. So as you can see, this omega GW is directly proportional to the Hubble parameter. So if there is any non-standard cosmological scenario that changes the expansion rate of the universe at any given point of time, then it will leave its imprint on the gravitational wave spectrum. And that is what we will see. The frequency of the gravitational waves as observed today can also be related to the temperature at which they were generated, and this frequency is directly proportional to the temperature. So if you have, the earlier you go in the universe, the farther back you go, the temperature is higher, so we will observe them in the higher frequency range. So this was just a brief overview. The two gravitational detectors that I will be primarily talking about are LISA, which is the laser interferometer space antenna, and ET, which is Einstein telescope. LISA is a space, both of them are upcoming missions by the way. So LISA is a space-based mission which has three spacecrafts flying in this equilateral triangular configuration, and their arm length is 2.5 million kilometers. ET on the other hand, Einstein telescope, this is an upcoming ground-based mission, and it also has three interferometers arranged in what is known as a xylophone configuration, again in a equilateral triangular formation. And the arm length for these is 10 kilometers. So this is just to show you a schematic of what these observatories are going to look like. What we are interested in is what are known as sensitivity curves. In order to detect a stochastic background, we need to compare it against the noise properties of the particular instrument, whatever observatory we are interested in. And the way to do that is to compare it against the sensitivity curves. These are the nominal sensitivity curves. And these are depend on the intrinsic properties of a particular experiment. Here I have shown you the one for LISA, and this is the one for ET. So if you look at the frequency ranges, you can see that LISA is most sensitive, as Rajiv also mentioned, in the millihertz range, while ET is most sensitive around 7 hertz. And this usually this sensitivity curves are calculated in a numerical fashion, and that gives you this exact dashed lines, dashed purple lines in both cases. However, for the purpose of our calculations, it is very useful if we have an analytical template to represent this sensitivity curves. The analytical template has been shown here in this solid purple lines. The one for LISA was already provided by the LISA cosmology working group, but in this work that I have referred to here, we provided one for ET, and I will explain to you how it is very essential for the purpose of calculations. It's very important to have such an analytical functional form for this sensitivity curves. So now let me introduce a quantity that you might already be familiar with, but I will just talk about it for because this will become important in the later part of the talk. These are known as power law integrated sensitivity curves. Basically what happens is, since we have a stochastic signal which varies over a wide range of frequencies, we can take advantage of this broadband nature of the signal and add to the total signal to noise ratio. So what you saw just before, this arises from the intrinsic properties of the particular detector. But then if we also add information about the signal that we are expecting to detect, what we end up with are these integrated sensitivity curves. So let us say we are expecting a signal to be of a power law form, or we want to see how the sensitivity would improve for a power law signal. Then we assume such a power law form with certain spectral index. Then we can integrate this here, a square of this, along with a ratio of the noise curve, the nominal curve which you have just seen, and we consider a certain value of SNR. Let us say we want a minimum SNR of 5, for instance. We put that value here and we take the total time duration of the observation. Then we can calculate this amplitude omega beta. If we choose a set of spectral indices beta, then we can calculate all the corresponding omega betas. What this gives us essentially is a family of curves. Then we can plot the envelope of that family, and that gives us the power law integrated sensitivity curve. The power law term comes because we are assuming it's a power law. If you see the plots of Rajiv, they can be very different. There can be very different frequency profiles, and then we have to change this accordingly. So this is the family of curves that we get for a power law case, and this envelope that you see in the solid blue line, that is the PLS. And here I have shown 3 plots for ET. This is the nominal curve, the noise curve that you saw before. If you look at the blue one, that is the PLS. As you can see, the sensitivity has improved a lot by a couple of orders of magnitude. And the red line here is the BPLS. That is, if we consider that our signal is going to be a broken power law instead, then there is a difference with respect to power law, and this is a very important distinction to make. And we talked about this concept of introducing a BPLS in this paper here. So there are certain modified cosmological scenarios, as I was talking about, which can change the inflationary tensor power spectrum, which is scale invariant, and this blue line here. It's scale invariant if you assume that it's if you assume that the initial primordial tensor fluctuations were a scale invariant. But in certain cosmological scenarios, such as here, where we have a scalar field domination, which is coupled to the metric with both a conformal and a disformal factor. For certain choices of these factors, we can amplify this primordial gravitational spectrum considerably, and this can, as you can see, this can reach the sensitivity regions of LISA and ET along with some others. And here, these plots that you see, these are the integrated sensitivity curves that I was just talking about. And just to briefly mention, in the same scenario, we can also, for a certain choice of initial conditions and parameters, we can also somewhat account for the nanograv result from that Rajiv was also talking about in detail. So now, as you have seen, these 2 instruments, they are not overlapping in their frequency range, but they are adjacent. And there are certain primordial gravitational wave signatures which cover a wide range of frequencies covering both of these detectors. In that case, our question is to see whether we can use the information from both of these detectors to improve the signal to noise ratio further. That is what we discuss in this paper that I have referred to here. So we want to calculate the total SNR if we combine the 2 detectors, if we combine the individual SNRs, and basically that is done by adding up the 2 SNRs in quadrature. And from here it is very easy to understand that the 2 detectors together can reach a higher value of SNR than the individual detectors would reach. And we are interested for this case in stochastic gravitational wave spectra which are enhanced within this frequency band, because this is relevant for both LISA and ET. So this can be tested for any kind of signal that you are interested in, but I will be focusing on a broken power law for now. So a broken power law signal, these are the nominal sensitivity curves. This is the improved. In the green line, I have the improved broken power law sensitivity curve, the integrated one that I was talking about. And if we consider a broken power law signal like this, which lies in the middle of the two bands, then we want to see if we can detect this better by combining the SNRs from the two individual instruments. So such a broken power law signal can be characterized in this way. So here, along with the amplitude and the break frequency, which is the frequency where the broken power law breaks basically, along with that we have these two spectral indices N1 and N2, which give you the spectral index of the signal when it is rising and falling. Along with that we have another parameter sigma, which tells you whether the signal is wide, whether the peak is wide or narrow. So we can optimize over all these parameters. What we see is, if we take an individual instrument and do a Fisher analysis of what the errors are going to be, we can see that an individual instrument can detect only one side of the spectrum, like it can only tell you with precision what the spectral index on one side is. So for this example, LISA would tell you the spectral index here, ET would tell you the spectral index here, which is easy to understand because it's lying in the between the two bands. But if we combine the information from them, then as expected it actually improves, and we can tell quite precisely what the spectral indices are going to be on either side, and this is especially very important to break degeneracies among various early universe scenarios. Now I will briefly talk about anisotropies in the GW signal, and I mean whatever I am talking about has been the isotropic component, but there can be anisotropies, and I will specifically be talking about kinematic anisotropies which arise due to the relative motion of the observer's frame to the GW frame. And this has been shown in this paper can be expressed in this form, where along with the isotropic component here we have this quantity P, which quantifies the anisotropic component that can arise due to this motion. And this is given in this form, which is related to beta. Beta is basically V by C, V being the relative velocity and N is the direction of propagation of the signal. So from here you can see that if this peak factor is 1, then we basically have no anisotropies, it's an isotropic signal. And also, okay, so usually when anisotropies are studied, this P is separated into two components, one depending only on frequency, one depending only on direction. But for kinematic anisotropies, we actually cannot use this separability concepts. So we do not consider this to be separable, and we can also consider any possible values of beta. So we can compute something known as the response function. This essentially is a way of telling how well a signal will be detected by the instrument. We calculate this for the Einstein telescope. Apart from all these contractions between the Einstein telescope detector arms and the velocities, we have these three coefficients C1, C2, C3 which quantify how high the amplitude of these anisotropies is going to be, and they involve various integrals over the P terms as well as the directions. But for a power law case, this can be evaluated analytically, and it only depends on the spectral index basically. Here you can see that if alpha is 1, then there is no anisotropy because the P factor will become 1. This is a very interesting result, that for a spectral index of 1, this gives rise to no anisotropies, no Doppler anisotropies. But for other values, we can evaluate it numerically. For example, I have shown you here what are the values if alpha is chosen to be 3. If the signal is different, then it cannot be evaluated analytically. For example, for a case of a broken power law, it has to be done numerically, and that is what we have shown here. For two different kinds of broken power law spectrum, one wide, one narrow, we calculate these three coefficients C1, C2, C3, which gives us the amplitude of the anisotropies. And you can see the narrower the spectrum is, which is the steeper the spectrum looks, we get a higher amplitude of these anisotropies, and this can also be seen in other types of spectrum. In this work that I was referring to, okay, this work, here we also do this for a double peak kind of thing, which was shown by Samuel yesterday for the scalar induced gravitational waves, and there also we see that the amplitude increases as it gets sharply peaked. So I will not be discussing this in detail because Rajiv has already done this for the case of scalars, and on Monday Shubhashish also discussed this for the case of magnetic fields. But secondary gravitational waves can be generated if we have primordial magnetic fields, and that we have worked on that, and let me not get into the details, but basically this source term arises from this primordial magnetic field contributions. And for certain choices of the non-minimal coupling function that is used for generating this magnetic fields, we can have an omega GW which reaches within the LISA band, and it should be detected, we expect it to be detected by LISA experiment in the future. So this is my summary. Thank you.
Thank you, Deepika. We have actually we have time for a few questions. So,
Hi, Devaki, very nice talk. Two comments maybe. One is that, calculated the stochastic gravitational background SNR for LISA. One of the major issues in comparison to what you do in LIGO is that you are not going to have uncorrelated noise. As a result, you have to do the global fit.
Okay.
So your power law integrated noise curve will get an additional budget because I have to estimate all individual sources which are a year long.
Okay.
So that hits up as an additional noise budget significantly because your noise is not uncorrelated. Same is also true for ET because you have a triangular configuration within a 10-kilometer regime. Your noise in the low frequency gets correlated because of seismic activities, which is not the case if you have two Ls at two different places on the Earth for ET, which is also a possible scenario.
Yes.
But this problem is much more severe for LISA. We cannot do the cross correlation.
Okay.
On the noise. So maybe you can also consider this option of global fitting of the parameters and get the stochastic gravitational back on it.
Okay, yeah. So I didn't mention that in detail, but I should have said that we are assuming some things when we calculate this. For example, for ET especially, we are assuming low frequencies, and also for LISA, we are assuming that we are doing the noise diagonalization and we are only taking that. So those assumptions are taken into account. If they are not taken into account, of course, the results will change, yes.
So just a bigger picture question, and it's also inspired by a question which Kaushik Datta had asked David Wrightsey at the ICGC. So question is, do the stochastic gravitational wave background also extend up to kilohertz and microwave frequencies? I mean, there are some people trying to build gravitational wave detectors at microwave frequencies. So do these models also extend up to such high frequencies?
For example, are you talking about the model?
In general, not specifically the models you discuss, in general cosmological models. So,
If it is like, if it comes from inflation, it would be covering all frequency ranges.
even at tens of kilohertz.
Oh, yes. Actually, there are certain experiments, I don't know what the status is, but there were some discussions about this ultra high frequency gravitational wave detectors. Yeah. So they are mostly arising from very early universe scenarios.
Deepika, is it right that that cutoff is determined by the reheating scale, right? Isn't it?
Which cutoff?
I mean, at some point the gravitational waves would cut off at high frequencies, isn't it? Given the reheating time of reheating.
Okay, yeah, maybe
reheating.
it depends on what the reheating scenario is going to be like.